Let's implement insert the function of the singly linked list. Let's have a brief test code first. So here we have an empty list just created using append. Let's put 1 and then 2 there. Then what we have internally is that here is a list object variable. It is 2 pointers, head and tail. And the data are wrapped by node structure. So we have a data 1, and we have data 2, and the first node is pointing to the second node. The second node null pointer, nothing after that. Then this one is a head of the list. This one is a tail of the list. So in this situation, as we call insert the function. So insert the function will take two arguments. First, let's give a position. So at position 0, let's insert the 5. That's the example. Then what should happen is as follows. So node structure wraps up data 5. And then this new one should be at position 0. Currently, this one is at position 0 and position 1, but this one should be, new one should be position 0, and this one should be position 1 and position 2 and so on. Then we need to rearrange the link such that the head, this is head of the list. Then new node just created should point to next node. Zone. Then we have a position 0, 1, 2, something like this. Similarly, we can call insert function for any arbitrary locations. Insert some data. Let's call it as 2. At position 2, let's add insert 7 there. Then new node should be created. And then 7 is stored there, and this one should be position 2 as we provide here. So currently position 0, 1 and 2 are there, so we need to rearrange this link. Now from position 1, next node is this one, then this node is pointing to this one, then this one becomes a position 3 and the like. Then to verify this code, we could use a get function. So assert m.get at position 0, we have a 5. The very first one is a 5 here. Then at position 1, the data is a 1. At position 2, data is a 7. At position 3, data is 2. So we expect this result. So let's implement the insert function in .h interface. Void insert. First integer is a position, second integer is a data. So pos data is the order. Then let's implement insert the function. Void class name, function name, position, data is there. First, let's validate the range of pos, valid range. So assert the position should be non-negative, 0 or positive for sure, and the position should be 1. Here, if you simply assume from array-based one, so we know that maximum position should be less than count or less than size function, whatever returns. But we have some special case that equal sign may be allowed as well. The reason is as follows. Say that we have a node at position 0, 1, and 2, and the like. So 0, 2, 2 is null. So we can insert data at the 0, which means the new one is inserted prior to current 0, and this new one becomes 0, and then the rest of the positions are incremented. Also, we can insert at any position like that 2, then there will be new 2, and then or link will be reorganized. Suppose we have 3 data, position 0, 1, 2, then can we do insert 3 with some data? Insert 3 means we add the new data, insert the new data at position 3. Currently, all positions are 0 through 2, but 3 means that we simply append it. If we append the new data, suppose this is 7 new data, then that will be position 3. So in insert function, valid position could be up to the size. So if we have 3 data currently, if a count or size is currently 3, in position is 0, 1, 2 only, but still we can insert at 3, which means appending new data at the end of the list. So valid range includes equal sign as well. So we have some special case over there. Then inserting, we may have several cases. Always, how do we figure out those several cases comprehensively? Then what will be on the left, what will be on the right as we insert new data. Based on you can figure out. So in list object, we have a front and the tail pointer there. And then those are used to wrap up those data. Then front node, and then tail node, and then between those there is a link there. The very last one is a null pointer. So we want to add a new node or insert a new node. Then what will be on the left? What will be on the right? Based on that, we can figure out the all possible cases we need to take care of. So here, those relations, let me draw that on over here so that we can continue to write the program. So new node, new insert, what will be on the left? What will be on the right? And then when is such case? So when we insert a node, we may insert here, where left hand side is list object and the right hand side is node. So left hand side is simply list object, right hand side is node. And then the case is when we insert at position 0. That is the case. Another case we could consider is that we could insert in between two nodes. So left hand side is node, right hand side is node. Then the case is that the position should be at least 1. So 0 is the first case. So position should be at least 1, and then it should be less than the very last position. If you insert in between the two, there should be something on the right. So the very last one is a count minus 1. So it's a count minus 1, less than count minus 1. So it should be 1 or greater or less than count 1. Then we are inserting between two nodes. Another case is that if we insert at the very end, which is append, then left hand side is node, right hand side is nothing. the case is position is the same as a count. We are appending a new one at the end of the list. And then there is another case. A special case is that if we don't have any node at all, at the very beginning list is empty, then inserting at position 0 means left hand side is list, right hand side is nothing. So this is the very first node entered. Then case is if currently Q is empty or size is 0, then that's the case. So we have 4 possible cases to handle that. So let's program those cases one by one. So here, first, if so let's take care of append case. We have implemented the append function already. Append means out of those 4 cases, append means we add the data at the very end, which is the third case, which is append. Also, if a list is currently empty, inserting the very first node is also append. So the third case and the fourth case combined is the same as a append function. So if the position to be entered is the same as a current size of the list, or if current list is empty, then we have third and the fourth case combined, then it's the same as append data, which we have already implemented. Else, if let's consider the very first case, then if a position is 0, and then second case is the rest case. So at position 0, we are going to insert, which means we are going to insert a new node over here. And to do so, we need to reorganize. So this is a front pointer, P front. So P front should point to new node, and new node should point to the existing first node. We need to rearrange these links. And actually, this operation is exactly the same as a push of a stack. Infinite stack implementation push is exactly this operation. So the push operation is we first create new node with the data wrapped up by that. Then new node link should be the address of the first node. The address of a first node is head, and then head should now point to new node. So that's a push of stack. In this picture, I've said this one is a front, but that's a terminology of a queue. In list, the terminology is a head. So now we have the remaining case, which is the most complex. So here, what you do is between two nodes, we are going to insert that. And between two nodes, since we have checked all of those conditions above, and then we are coming down to this else case when there should be at least 2 nodes. And then we are going to insert a new one between the two. That condition is satisfied from the above all cases. So let me draw the picture again to take care of the rest case. So we have list object, which is a head and tail pointer. Then we have a nose. let's assume we have a 4 nodes. Then front pointer, the tail pointer is there, and then links are established between nodes like this. What you want to do is we want to insert a new node. Currently it's a position 0, 1, 2, 3. Suppose we are going to have a new one at position 2. Then what you need to do is this current link from 1 to 2 should be broken. Then this node 1 should now point to new node, and the new node should point to existing node at 2. So we need to this kind of arrangement. So in this operation, what we can find is that we need to know this variable, the variable at node 1. This is link variable at node 1. So this variable should be updated by a new node address. And then at new node address, we need to write address of node 2. So to insert a new node between 1 and 2, what we need to know, what we need to have minimally is a variable, this one, it's a link variable of node 1, and then address of node 2. So those two things are needed, and then you can rearrange the node. Then how do we find that one is if we know address of node 1. We are going to insert the node at 2, so one previous position. If we know the address of node 1, suppose that is n, address of node 1 is n, then this member is n arrow link. So in this, we can write a new address created for node 2. And then address of node 2 at this moment is stored at this one. So if I know the address of node 1, then I can have access to this member by this syntax. Also, in this variable, address of node 2 is stored. So to rearrange those links, minimally what we need to know is address of node 1. That is address of one previous node to be inserted. So given pos, if it's 2, we need to know address of node at 1. So 1 less pos. That's the goal. So in this case, the remaining case, we need to first find the address of one previous node to be inserted, one previous of pos. So that is computed using a loop. So let's prepare for that. So before we do anything, let's create a new node with a data wrapped, and then this one represent the red node to be inserted shortly. Then let's find the address of a left node. Left here means left of a pos node. Address of a left node. Let's begin with the head at the very beginning, and then let's have a loop. For pos minus 1 times, we are going to jump the link. So beginning with the 1, pos minus 1, then this for loop will iterate pos minus 1 times. In pos minus 1 times, left is updated by left link. Then we jump through the link by pos minus 1 times. So when the loop is done, the variable left is holding address of left node to be inserted. Then address of right node is in left link variable. So the goal is now we need to rearrange those links such that left and then new node just created and then right node. That's the arrangement of the links we need to do. So to do so, in the new node link should be the address of an existing node of a POS that is in left link. Then left link should be pointing the new node. So that's the arrangement. Then, of course, we need to update the count. Also, in the previous case, we forgot to update the count. So this is the implementation of a list function. Let's verify that. So invalid. So here in I is initialized to 1. Okay, there's a syntax error. Compile the program, and then as we run, the minimum test code is successful. The test code was in main.cpp. We begin with the two data appended, and then we insert those ones at given positions, then we verify that. So at this moment, some minimal features are satisfied. So in the next video, we continue to implement some other functions of a linked list.